So we have used this concept of continuity in pre-calculus. I know that you have discussed things that have been continuity. At least people have used phrases like discontinuities already. So if you know what a discontinuity, you kind of have an idea of what continuity is. So what I would want to ask you first is, how do you define continuity as you know it right now? So if you had to describe a function that's continuous, how would you describe that? There's no breaks in it. Okay. We can what? You can draw it without lifting your finger. Love it. All right. So I don't know about you, but this is a math class, and when we start trying to define something about how we draw it, and there's nothing wrong with those particular explanations because we've never actually had a definition, right? And we haven't had enough information to make a definition. So saying something like we can draw it without lifting our finger. Well, even then I can draw something that's continuous that's discontinuous. Look, I didn't pick up my finger. What? It's like the curse of Graphio. All right, that was really. But the fact is that when we draw it, trying to define something as math as how we draw it seems a little weak, right? But that's a really good functional thing. There are no breaks in it. So now I start asking, well, if we look at that previous one, was there really a break? We have to define what a break is. I like the idea of break because I think we could actually come up with some really good things for that, but we'd have to define what a break is, right? So we are now officially at a point where we can come up with a true mathematical set of rules so that we can sit there and look at a problem, and without having to graph it, without having to see some sort of visual representation of the problem, we should be able to look at something and to say with certainty this function is continuous or this function is not continuous at a point. So we have this statement: a function f is said to be continuous at x equals c if and only if. So if a function is continuous, it will have these three properties. If the function has these three properties, it is continuous. Awesome. Good old biconditional statements. So we talk about continuity at points. Let's probably use the most obvious out of the three conditions. A function is going to be continuous if f of c exists. If you don't have a point there, is not continuous there, right? We would say in this case we're checking to see if the point exists. Second thing we want to be able to prove. If the point exists, we also want to make sure that the limit exists. If the limit doesn't exist, then we know that there's either a jump or an asymptote. That's not something that's continuous again. So we need to check limit exists. There's one more thing that we have to take account. What do you think is another important thing? I need to know if a point exists. I need to know that the limit exists. There's something else that's really stinking important when it comes to continuity. Could I have something where the point exists and the limit exists, but it's still a discontinuous function? So there would be no jumps. At that point, the point still exists, but I still have a discontinuous function. So no jumps. Asymptotes are also not going to work in this particular situation. How would I draw that? So if a limit exists, what does that mean? That means that at some c value, we know that this has to come up like this and that this has to come over like this, right? For a point to exist, I need to have something on that spot. But what if it looks like that? Does the limit exist? Sure. It's where the hole is. Does the point exist? Sure. It's where the dot is. Well, that is actually a function. And it's a function because remember that the open circle is not actually something. What's the problem with that graph? I've satisfied both of my first two conditions. What's the issue with my conditions? Well, there's this third condition. The third condition deals with condition 1 and condition 2. Well, if you can't figure this out, we're going to have trouble. Let's think about it. You got time. You don't have to know the answer immediately. This is math. Math took, a couple thousand years to come up with. I mean, heck, we've been doing math since way into the BC and BCE, depending on what you want to call it. This is new stuff. This is like from the late 1700s. What do we think? My limit's here, but my point's here. Point has to be on the line. If the point were on the line, what can we say about the point and the limit? No? There it is. When we put the point on the line, then the point and the limit are the same thing. If the point and the limit are not the same thing, we have a problem. The point must equal the limit. Good stuff. So I need to make sure there's a point. I need to make sure that there's a limit. And I need to make sure that those two things are the same thing, because if they're not, then we got all sorts of problems going on around here. This leads to the three types of discontinuities. You are probably very aware of all three of these. What does a point discontinuity look like? It's a hole in the graph. It's what we literally just drew up there. Woo! Look, there's a hole. I'll tell you what, I'll even put a point there. If we look at a point discontinuity, where could we have possible failures? Which of the conditions will a point discontinuity fail? Could fail condition 3. It could also fail condition 1. Condition 1 would be this picture is a condition 3 failure, but if we would have erased that point, it is now a condition 1 failure, because you really can't fail condition 3 if you don't satisfy condition 1. So we could have a situation where we fail condition 1 or 3 right there, and we could have what's called a point discontinuity. Interestingly enough, these are also given a different name. These are also called removable discontinuities. We could actually theoretically just plug in that hole or move the point to that hole, and then suddenly everything is fixed. We plug the hole, look at that, we've removed the discontinuity, everything's great, we're happy, we move on with life. So these are also called removable discontinuities. The second of the discontinuities is the jump discontinuity. What do the jump discontinuities look like? Yeah. Boom. We go, we stop, we hit another point, it does something, it's great, right? At the C value, here's my C. At the C value, we do that. Which of these do we fail on a jump discontinuity? Always fails condition 2. It could also theoretically fail condition 1, but the important thing in this jump discontinuity is that it will fail condition 2. Finally, there's asymptotic infinite discontinuities. As you've probably guessed, especially since I put a little thing down here, that's a situation where we have. Now what's interesting about this is if you were to write this, and if I were to ask you what the limit as x approaches c is for that particular function, you would actually write on your paper what? You'd probably write, in my picture, that's infinity, right? If they both went down, you'd write negative infinity. What we need to remember is infinity and negative infinity are technically D and E's. So again, this is another failure. Condition 2. There we go. Not too shabby. So we've got 3 types of discontinuity. We've got all of this. I do want to make a point as an aside here. Down here at the bottom, I do talk about continuity over a closed interval. So instead of going from negative infinity to infinity, I may be looking at continuity. For instance, in this problem, what shape does that particular function make? It would not be a line. Yeah. Should be a curve, but specifically semicircle. This is a semicircle. For those of you who don't know that, now you do. So that's a semicircle. It's a semicircle with a radius of what? 5. Fantastic. It's not too hard to tell that this is continuous at, say, 0, or at -1, or at +3. But if I ask you if it's continuous at x equals 5, this gets into some weird gray space, and typically I've never seen them ask a question about endpoint continuity. But this creates some gray space because, of course, for a limit to exist, we have to be able to approach the limit from both sides. But if I ask you about x equals 5, there's literally nothing that exists to the right of it. We will say this has endpoint continuity. Endpoints, we're just going to look from the one-sided limit. We're not going to do a full limit because the other side legitimately just the data doesn't exist. So there you go. Useful information. However, if this were an open circle, then this could be discontinuous because there would not be a point at that spot. What? I know. All right. So here we go. We're going to try to get through at least 3 of these. Let's see how we do. All right, we are going to discuss the continuity of the function below by identifying and justifying what type of discontinuities exist, and we are going to sketch a graph. Ladies and gentlemen, the first thing I want to know is this function, they do have discontinuities, there's the word I'm looking for. Where would the discontinuity exist in f? At x equals 2. We know that f of 2 does not exist. Fantastic. So my question then becomes, what type of discontinuity is it? We know that it failed existence, but is there a limit as x approaches 2 for this f of x? So what we would have to do is look at this. Okay, we sub in a 2. This is 2 squared minus 4 is 0. This is where we start going, oh crud, we're going to do extra work. Look at the denominator, 2 minus 2. It's a 0 over 0 situation, which means we are going to have to do some work here. All right, we can look at this and we can factor. What is the factors for the numerator? And when I look at this, this is suddenly going to take the shape of the line x plus 2, which means my limit as x approaches 2 is
2, 4,
6, 8. So, obviously, do I have to check condition 3? No, that'd be silly. We don't want to be silly. We know that there is definitely a limit here. So at the point 2, 4, there is a hole. That's what we've identified. What shape is this function going to take? It's going to be a linear function because the leftover term is linear. Increasing or decreasing? Come on now. Increasing, positive slope, positive or negative y-intercept?
negative, positive.
Boom. By the way, this is a sketch. I do want your sketches to be at least semi-accurate. What I mean by that is it does not necessarily have to be to scale, but if the function is supposed to be linear and increasing and have a positive y-intercept, please draw something that is linear, increasing, and has a positive y-intercept. There's nothing worse than when I ask this question and I ask you to sketch the graph, and I have literally had somebody that from this graph got this. So I'm just saying, make sure that you draw something I think it was positive though, doggone it. We got something there. So when we say discuss the discontinuity, all I'm asking you is to state that this has a, what type of discontinuity? A hole. So out of the three, this is a point discontinuity. At x is equal to 2. That's what I mean when I say discuss a discontinuity. Awesome. Let's check out the next one. First thing I'm looking for, where is the discontinuity going to occur? Definitely at 3. Why? Because I know that f of 3 does not exist. So this is at least a point discontinuity, but most of you are pretty smart on these, and you could probably already tell what that graph kind of looks like. Hopefully. What about the limit as x approaches? Oh my goodness, 3 of f of x. We will go through these tomorrow. There is absolutely no formative tomorrow, but you may want to look ahead at some of these. I would like you to actually sketch this graph, and I would like you to take on the next one. Tell me about it. All right, thank you folks. Have a wonderful day.